In this tutorial, I will be discussing approaches used in aggregate planning to determine a production schedule to meet an uneven forecasted demand. The first approach, the level approach, is one in which the production is set to a level or constant amount which would be equal to the average forecasted demand. The second approach, the chase approach, is one in which the production level is set equal to the forecasted demand in each period, resulting in quite an uneven production schedule. Then I will use one of those as a starting point to manually optimize and try to determine a production schedule with even a lower total cost. Finally, I will use the transportation method or linear programming to determine the optimal or lowest cost production schedule. I have already made copies of two templates from the files of templates which are provided with your textbook, the aggregate planning template and the transportation model template from the same chapter. Starting with the level approach, I'll utilize the aggregate planning template. Note that I've already cleared the data and set the number of periods to 6 for this example. Entering the forecasted demand which was given, note that the demand ranges from a low of 200 to a high of 500 with a total of 1,800 over 6 periods. Next, I'll enter the cost of production and inventory. Producing on regular time costs $2 per unit, and there will be a limit of 300 units per period. Producing on overtime has a cost of $3 per unit, and there will be a limit of only 40 units per period. Subcontracting has a cost of $6 per unit and essentially no limit. Inventory forward costs $1 per unit per period. Back ordering, that is producing in a later period to meet demand in an earlier period, has a cost of $5 per unit per period. Notice at this point we haven't produced anything, so everything's a backlog and we're building up a huge back ordering cost. We can fix that in a hurry by producing on regular time. On regular time we are allowed 300 units per period, which is the average demand of 1,800 over 6 periods. That will meet our total demand. We produced 1,800 to meet the forecasted demand of 1,800. Notice that our inventory built up during the first 3 periods dropped and was 0 by the 5th period. We incurred back ordering in the 5th period of 100 units. Our top graph shows that during the first 4 periods, our forecast was below our production, meaning that we were building up inventory as stated earlier. Then in the period 5, our demand was higher than our production, which resulted in the back order that was necessary in period 5. In our second graph, we can see that our regular production cost is steady at $2 per unit for 300 units. We built up inventory over the first 4 periods, and in the 5th period, we also had a very high back order cost for a total cost of $4,700 for that production plan. Let's rename this template to reflect the level approach. Okay, now let's use the chase approach to come up with the second production schedule. I'll start by copying the level approach, which we just finished. And I'll name my new template Chase. The demand stays the same, as do the costs for production and inventory. The production level, however, will be quite different. I want to produce at the same level as the forecasted demand, which will result in 200. So the first 3 periods can be met with regular production. In the fourth period, we are unable to meet that with regular production, so we need to produce 300 regular, 40 overtime, and we're still short 60 units, so we need 60 units of subcontracting to meet that demand. Similarly, in period 5, we have 300 units allowable of regular, 40 units of overtime, and we're going to need a whopping 160 units of subcontracting. And finally, in the sixth period, we only need 200 units of regular production. So we have met our demand through the use of all three production methods. We have produced 1,500 units on regular time, 80 units on overtime, and we have required 220 units of subcontracting. We have used no inventory and no back ordering. Notice that the forecast and production lines fall right on top of each other because, of course, we are producing at the same level as the forecasted demand. Also notice in the second graph, our regular cost is relatively low for the first two and the sixth periods. Then in the fourth period, we incur overtime and also a relatively large amount of subcontracting. But our total cost at $45.60 is still less than our total cost for the level approach. So we have found an improved production schedule by using the chase approach. Our third step is to start with one of our first two approaches and try to improve upon it and find a production schedule with a lower total cost. We'll start with the chase approach since its overall cost was less than for the level production approach. I'll make a copy of that template and we'll call this the improved template. And the obvious thing to improve is this high cost of subcontracting. We'd like to remove those 220 units. A very easy way to do that would be to produce more at regular production way back here in periods 1 and 2 and carry it in inventory. Increasing this to 300 and 300, that leaves us only 20 short, which we could pick up as overtime. And then we can eliminate the need for subcontracting. This has brought our cost down to $43.80. We can see that we end with 0 inventory and 0 backlog, so we have satisfied demand. Okay, finally we're going to use the transportation method to see if our production schedule can be further improved. In the transportation model template, I have already filled in the input matrix and deleted the values from the solution matrix. In the input matrix, in the body of the table, we have our costs. Let me delete a few values to demonstrate how they are entered. In period 4, if you produce to meet demand in the same period, there's a cost of $2 regular time, $3 overtime, and $6 subcontracting, the same as before in our aggregate planning template. If you carry inventory forward, that costs an additional $1 inventory carrying cost per unit, which will yield $3, $4, and $7 per unit. Carrying back, that is producing in period 4 to meet demand from period 3, that's back ordering, which will incur an additional $5 per unit charge for $7, $8, and $11 for regular overtime and subcontracting respectively. Continuing that, we'll fill in the rest of the costs for that part of the table. The bottom row is the demand, which are the same values as we entered in the aggregate planning template, with the exception of the last column, which is essentially a dummy column used to balance the problem, use up the extra supply. In each period, we have a supply of 300 on regular time, 40 units on overtime, and a large amount, or using 600, for subcontracting. To solve the problem, we simply press the Solve button. This is a quite large linear programming problem and takes many iterations to solve, and a checkpoint is reached as indicated here, but continuing will reach the solution in a short amount of time. And our solution gives a total cost of $43.60. And as you can see, we were very close on our previous production schedule at $43.80. Let's investigate what changes would reduce the cost by that extra $20. In the first period, we only used, in this solution from the transportation model, we only used 200 out of the 300 of regular time production. In the second period, we used all, there was no unused, so we used all 300 units of regular production, but no overtime and no subcontracting. And that's the same value we had before. In the third period, we again used all regular time, and we also used all overtime and no subcontracting. So we need 40 units to use our entire allotment of overtime. In the fourth period, we used all our regular time, all our overtime, and again, no subcontracting, which are the same values we had before. In the fifth period, we again used all regular, all overtime, and we used 80 units of subcontracting. So we need to add back 80 units of subcontracting in the fifth period. And finally, in the last sixth period, we only used 200 units out of 300 of regular time production, which is the same as before. So by making those changes in our aggregate planning template, we have reached the optimal solution. As it turns out, this is one of many alternate optimal solutions, all of which achieve a total cost of $43.60. And that will conclude this tutorial.